All right, welcome back. In this video, we're going to continue our discussion of designing beams or analyzing beams that contain web reinforcement. And so we're going to walk you through a general procedure. We're going to use simply supported beams as our basic example, but the approach works the exact same for continuous and other applications. But we're just to kind of grasp our idea about the different regions that show up. I'm going to walk you through a methodology that I use in order to be able to construct a set of diagrams that will help me be able to determine the size of the stirrup and the spacing of that particular stirrup. Okay, and so the way that this starts to work, set itself up is that we're going to start by looking at a selection of a simply supported beam. Okay, it's going to have some span of whatever it is. Okay, and we're going to be basically looking at a half span of this. Okay, so this lowercase l, if you will be kind of a script L is often what's used. Okay, and so we've got a uniform load, and so we know our shear diagram, just like we talked about in the last video, ends up being this triangular pattern, and we know that at the center line of the support, which is this point, we have a value of VU max. Okay, but the design at the critical section we know occurs at a distance of D from the support. So this distance down to that guy, get my pencil lead set up here. Okay, that distance is D. Okay, and then we pick off the shear off this diagram. That's the critical shear that we have to design for. Okay, all right. So we're going to take a look at, I'm going to show you we talked about two different methods for estimating concrete strength, in the simplified method and the detailed method. I'm going to start with the simplified method and kind of show you what these curves and what these requirements start to look like. Okay, so if I draw that half span, okay, again, I'm only going to the center line of this. So, and for a simply supported beam, this will be a mirror image over on the other side and negative. And positives and negatives in steel don't make a lot of difference. Okay, but what we have, all right, so the major players that are happening in this is that the first line that we draw is actually the shear diagram for our particular member. And so that would be this line. You see a little bit of a dotted portion here, and then it's solid all the way down, and it crosses zero at that center line location for a simply supported design. And so what we have then is that we know that was VU max, and that's this location, this number one, if you will, is the center line of the support. Okay, and then a distance of D, that's where VU occurs. That's our critical section. All right, and so what ACI allows us to do is it allows us to basically say from D to 0, make that constant. So I take this value and I basically draw this solid line here. Okay, and so I'm neglecting this, but again, we're counting on arching action or something to get the force above those cracks into the supports. So this isn't much of a concern for us. That this is our critical value, if you look. All right, okay. When you're analyzing this, the simplified method, or really any of the methods, say that there are two horizontal lines that you need to draw. Okay, if you remember from the table for AV min in the last video, we had a VC over 2, or in this case, that's half VC, or VC over 2. That's this guy, right? Then I'm going to draw a line at the VC over 2 capacity value, and I'm going to draw a horizontal line all the way across the entire diagram. Okay, and then I'm going to draw another horizontal line at VC, well, phi VC. Okay, notice there's a phi on this one also. Okay, a horizontal line here. So basically what I've done is I've broken this diagram into 3 regions, right? There's a region that's here, region 1, there's a region here, and then there's a region 3 that would be that guy. So those are the three bands. Okay, and all I do is I take these lines and I extend them to the point where they cross that VU curve. All right, and so at this point, that's the critical point. I take this VC line and I extend it, and it crosses here. Okay, and if I look at that, from here to here, this region, VS, is greater than phi VC. Okay, or sorry, that VU is greater than phi VC, right? We got VU greater than phi VC. Okay, then everything that's in the shaded region accounts for a VS value. Okay, so whether it's here, it's this distance. If it's here, and you notice that it changes, that this phi VS, the amount that's required for the stirrup steel to hold, changes with position along the length of the beam. But this is where I have to provide stirrups at some, required spacing, other than the minimum stirrups, if you will. Okay, so that gets us for that first zone. I guess I called it zone 3, but that shaded region, that's the criteria for that. Okay, for the region between here and here, what we called is our zone 2. Okay, I take the lower line, that VC over 2 value, and I extend it to here. Okay, and again, these are horizontal lines, and so between this point and this point in here, the minimum requirements are going to control. Okay, okay, that we're going to have minimum stirrups located at our S max limit as set by ACI. I have to provide in this range. Okay, and then technically, once I get past this point, I'm now below VC over 2, and ACI says when that happens, when you're less than 50% of what the concrete can carry, I'm allowed to just neglect stirrups altogether, that there are no stirrups required. Now, in practice, in my eye, normally I don't do this region. That if I need it here, I will take minimum stirrups and just extend it for there, just kind of as cheap insurance, because by this point you're getting out to spacings of 16 inches, 24 inches on center. You know, for 4 or 5 extra stirrups, I get a little bit of extra insurance out in these lower regions. But you don't have to. ACI says you don't have to, but just again, from a practical standpoint, I typically do. Okay. All right, so these become our 3 basic regions, and this is the shape of the category. This is what happens with the simplified method. Okay, and again, remember that VC in this equation is being taken as 2 square root F prime C BWD for a rectangular section. All right, so I put a 0.75 on that, and these are the lines. You've got everything that you need to know. All right, if we compare that to the detailed method, okay, you'll see that it looks very familiar. Okay, except now, I've got a bit of a glare going here. See if I can get there. Okay, I think that's a little better, still a little bright. Okay, the detailed method is very similar. Okay, again, here's my curve for VU. Here's my critical section and that cap line. Okay, but the critical section, or the limiting lines that you draw for the detailed method are, I have the bottom one, that's that VC over 2 value. That's no different. That gets me to here, because that's what's setting no stirrups required. Okay, but what happens now is that for the detailed method, that second line is a little bit different. Instead of being, you know, just VC, it's now 3.5 square root of F prime C here, but then you get kind of this curved relationship that shows up out of there. So what happens is that I save a little bit of stirrup steel in the shorter region, you know, more towards the higher shear values. Okay, because remember, in the simplified method, this was limited to 2 root F prime C. So I can get away with less steel according to the detailed method, but it's a lot more cumbersome to calculate. Okay, and then I have to worry about what am I doing with all of this, and so there's a little bit of a difference there. But overall, the general approach is exactly the same. You can kind of see why we like the simplified method, that these 2 horizontal lines are just really easy to draw, and that's why we're going to focus on that one. Okay, so anyway, those are our method. Okay, so that was figuring out the regions where web reinforcement was required. So again, in our picture, these shaded regions is where we have to give non-minimum web reinforcement. Okay, all right. Okay, step B then is we're going to locate is the location of maximum shear for the design of beams. Okay, and this gets back into our critical section. The shear strength of a section is increased if a reaction produces compression in the end region of a member. Okay, that's basically what we were saying. ACI 9.4.3.2 allows sections between the support and a distance of D from the face of the support to be designed for the same shear force. That's that flat region on VU. Okay, this is because of the cracking that we talked about a couple of videos ago. Okay, at a distance D, except when a concentrated load occurs within that region. All right, so now the commentary of 9.4.3.2 gives more details. They actually include a graphic that kind of illustrates these critical locations for shear. What they're saying is as long as I don't have, you know, for a distance of D, this is our simply supported beam, a D from the face of the support, and notice that they're calling base of the support as being the base of the bearing, not necessarily the width of the column. So if you have a very wide column with a very small pedestal on top, you go to the pedestal dimension, not to the column dimension. Okay, all right, so this becomes my critical location. What this criteria, it's a lot of wording that basically says I can go D from the support as my V value unless I have some concentrated force within that region. If I have it within that region, I'm not allowed to do it. I have to design for the full VU max. Okay, so we have to do something a little bit differently there. But for most cases, typically that's not an issue. You're talking, 12 inches, 2 foot from the end of the beam. Typically, I mean, you can have loads there, but they're not as common as being out in the middle somewhere. Okay, all right. So if we look at, and so these are the different scenarios. Here I have a beam that's integral with a column, and you can see that on this side, VU is a D from that face, and on this side, the VU is at a D from the other face. Those become our critical sections, and you would design this side one way and this side on its own merits and the other way as well. Okay, and then we get some other issues for, the concentrated load. This is that concentrated load within a D region. We have to account for what the actual V is going to be from the shear of that point load. because I can get a real high spike just from that extra load kicking in right there. Okay, so anyway, but that's all in 9.4.3.2. You'll see that graphic in the commentary if you flip over. And they have some extra writing that they'll talk a little bit more about what's going on. So anyway, but I show that to you for what it's worth. Okay. Okay, now, the third point that we need to look at, what we're calling as point C, is we're going to talk about different types of, common types of web reinforcement that occur. Okay, the most common by far is the stirrups. These are those U-shaped stirrups that we were talking about, whether it's two-legged or a multi-legged or something that, that's going into, into some cross-section, within a particular cross-section in that plane. That's where we're putting the stirrup steel. This is a stirrup. Okay, typically they're tied to the longitudinal steel, and then there's usually some sort of bar running in the compression just to help hold the stirrups up. Because if I don't lock this guy down with something at the top, it becomes very unstable when I place the concrete, and these guys can kind of lean over and not stay in their position. All right, the dimension that matters for us is this S, which is the spacing between these. Now again, S is going to vary as you move down the length of the beam, typically. Okay. But that's by far is the most common. Another method of web reinforcement is welded wire fabric. Okay, and this is a kind of a precast and kind of a mesh or a net-looking piece of metal. Okay, and it's very common in precast because for speed of construction, I can drop in a whole bunch of bars horizontally and vertically and get the areas that I need this way. For typical reinforced construction, they build the stirrups separately and install them one by one. But in a situation where time is of the essence, the welded wire fabric can work. And typically the shear values are, they're being required for VS are a lot smaller than this because most precast operations are obviously pre-stressed, and that greatly increases your shear capacity and reduces the amount that you need for the steel. So that's another method. There are times that I've seen where they've done some sort of inclined stirrup, okay, which is kind of a stirrup that's at this angle. And normally this is created by taking a longitudinal bar, and then for reasons that we'll explain when we get to development, taking this bar and then bending him up into the top and then using that as my stirrup. Okay, and I can actually eliminate the stirrup altogether by running this bar that way. Okay, and there are reasons to be able to do that. Okay, so that's our incline stirrup. Well, it's basically the same as an incline stirrup. An incline stirrup is taking the single stirrup I had here and turning him over at some angle. I don't see that very often, but I do see the longitudinal bent bars as a common approach. Okay, and basically we're taking the bottom bar and bending it up to work as a top bar. In that region, I've got a stirrup now that's that bar coming across. Okay, and normally this angle is somewhere greater than 30 degrees. You can't be really, really flat on that as we look at it. Okay, and then the other one that's used typically in columns or in seismic regions is some sort of spiral. Okay, in which it's a single bar that's kind of wrapped, kind of like a corkscrew or that slinky pattern, if you will, that goes all the way around and it comes around the bars and wraps. So here's my column, and I'm basically taking this bar and it just kind of spirals its way down. Okay, so those are the typical types of reinforcement. For what we're going to work at in this class, though, we're going to stick mainly with stirrups. Okay, all right. Okay, now next topic then is the functions of the web reinforcement. Okay, part of the shear force is resisted by bars crossing a diagonal crack in axial tension. Okay, that's the purpose of it. The web reinforcement, basically what it does is once the crack forms, the web reinforcement is activated, and it will keep that crack from growing too wide. It keeps the crack small. Okay, so it restricts the growth of diagonal cracks and leaves more area, okay, basically at the head of the crack to resist our shear and compression forces. Okay, it's also used to restrain splitting of concrete cover by the dowel forces, right? So if you remember the dowel forces we talked about in the last video were the longitudinal bars coming out, and I push down on the end of that bar with a V, that it's going to want to kind of pop the bottom of this thing off. And so by putting a stirrup around that bar, it helps hold that bar in place so that I get the dowel forces, but I don't get that prying action where that crack tries to turn and come this way and break off the bottom of the beam. So it's a kind of, it restrains that splitting behavior. Okay. As we talked about, web reinforcement counteracts the widening of the cracks so that the two crack faces stay in close contact. Okay, this is going to help maintain a certain aggregate interlock shear resistance. Again, if I can keep those cracks, and again, the other component of cracking was if this is two sides of a crack that has started to open up, when the crack is really small, these jagged edges kind of interlock with each other on either side of the crack. But it's the problems come when this crack becomes too wide that those guys don't capture. So I can get some extra capacity that we're not counting on by keeping those cracks small. And that's what the web reinforcement's doing, is helping to kind of hold things together. Okay. All right, so those are kind of the reasons why we're doing it. Now, some of the detailing requirements we've talked about a little bit, okay? And so we're going to go back to ACI 25.7, and basically the stirrup detailing requirements are to prevent shear failure initiated by failure of the stirrup anchorages. The ACI code requires the following, okay? That each bend away from the ends of the stirrup has to be wrapped around, okay, around a bar. Okay, you can't just have just a flat termination on this thing, right? So for a U-shaped stirrup, I have to bend around some sort of bar up here. And part of that is because if I don't have that wrap around here when I apply a shear load, okay, what happens is this bar wants to kind of pop out under the shear load. And so I can spall the side of this thing off if that distance becomes too small. But this wrapping around kind of helps lock that in place. And a lot of times we go to this 135 degree wrap, okay, where we kind of bend it down and then it's really locked in. And that's typically the way a U stirrup is developed. Okay. So this is kind of what we have. And so what they're talking about is that even, you know, in the case where like I have a bar that's doing a really funky pattern here, if we look at the stirrups here, I have to put a bar here and here in order to keep, because again, if I take the stirrup, if I apply a shear load across this section, as these pieces pull down, it wants to straighten this thing out, right? You know, so if I need that 90 degree bend, I got to put a bar there to keep it from wanting to go into that pattern, okay? And it will do that very, very easily. So we want to kind of protect that whole straightening out. And then in cases where I have kind of reentrant corners, this is like the bottom of an ash toe bridge girder or something, in which I have stirrup steel in the web, and then I have this wrap around the pre-stressing strands at the bottom on there. You get into a danger zone that's here, okay, in which, you know, again, imagine taking that bar and pulling up on it with a force V on this. You know, it's tied in, anchored here, okay, it's going to want to straighten out, and it can pop that side off. Okay, so this is not permitted, okay, since the tension in the stirrup will strengthen or will straighten the bend, pulling that shaded piece out of the position. So again, these are all just kind of some graphics of what's allowed and what's not. Okay. Okay, so that 25.7.1.3 then, again, is going to require a standard hook and an embedment length for free ends. Okay. Okay, the standard hook, like I say, greatly reduces this, and we'll talk about this embedment length when we get to developmental length discussions in the video that's coming up when we get to, like, I think it's like chapter 5 or chapter 6 in the book. Okay, and so when we do that, okay, so these are the kind of the standard hooks. Okay, you know, so we've got standard hooks on these corners. Okay, and if I decide to terminate it, I'm also not allowed to terminate any less than 12 bar diameters from the point at which I made the turn. Okay, and again, that's to give you a little bit of stiffness so that it's able to be fully anchored and you can get the capacity that you want at the location that you want it. All right, so those are some of the detailing procedures. Okay, so let's kind of walk through a general design procedure for what we're going to do as we start to kind of look at this. Okay, so for item number 1 that we have to do, we have to determine our factored shear diagram, VU. And again, I walked you through the diagrams of what we're looking at, and we're going to figure out the following values that we need to look at. We're going to determine VU. We're going to compute VU at our critical locations, and then we're going to calculate VU less than PVN as our capacity requirement. Phi is 0.75 and VN is VS plus VC. Okay, so that's our basic ACI characteristics. Okay, so the first thing I'm going to do is, or the second step, I guess, item number 2 is we're going to calculate VC. And you can do that again either using the simplified method or the detailed method. And so typically I use the simplified 2 root F prime C BWD. Okay, and the detailed method where VUD over MU is less than or equal to 1.0 is the limit on this detailed method. Okay, all right. Okay, other requirements that are hiding out there is that if no steel is provided, you're not allowed to take square root of F prime C as any value larger than 100 PSI. Okay, because, you know, back in the day, concrete strengths were fairly low, you know, 2,000, 3,000, 4,000. But now, ultra high strength concrete, we're pushing 14, 15,000 PSI. Okay, and so what they're going to do is they're going to limit, basically, this requirement basically says that F prime C on this can't be any more than 10,000 PSI if no steel is provided. You can't count on any more capacity than that. All right, and part of that has to do with, I think, with some of the aggregate interlock mechanisms and higher strength concrete, the aggregate crack interface ends up being very, very smooth. It's not as jagged as it would be at lower strength, so we can't count on much of it at all. Okay, and then the last requirement is that if you're in a seismic region, you can't count on the concrete for anything. Okay, the VC is 0 in seismic regions. Okay, and the part of that is because of these reversals, and that once I crack it, I can't uncrack it. So we're just going to neglect the concrete contribution altogether, and the steel has to do all of the work. Okay, which again, remember, we have a limit on VS max. It's running around in this thing, right? The VS max is 8 root F prime C BWD, right? If I don't have any VC, now my maximum can only be 8 root F prime C, not the 10 that we were looking at in the last video. So that's a big characteristic. So in seismic regions, you'll get bigger, bulkier sections because I can't count on the concrete for anything, and I'm maxed out on my steel size. So that will drive up BW and D as a result. And so that's one of the things, one of the extra provisions for seismic. All right. So then the third step in our procedure then is that we're going to plot the region where web reinforcement is required. Okay, so just like we talked about, we're going to calculate VS in terms of VU over phi minus VC. Okay, and then we're going to check at this point that VS is less than or equal to 8 root F prime C BW. That's that geometric dimension I just showed you. Okay, if not, if you fail this check, you have to change B or D. F prime C doesn't get you as much as changing B or D does usually. Okay, so you got to be kind of mindful of this limit. Okay, and again, if this is a seismic region, VC is 0, that's the check that you're making anyway. So this is our characteristic. Okay, all right. So then once we have that figured out, then we can go in and we can design our web reinforcement. Okay, and so our vertical stirrups, okay, the capacity from the stirrups is, for VS, is going to be AV over S times D times FYT. Okay, so if I know D, that's the position of the longitudinal bars. FYT is the tension in the stirrup, or the tensile stress of the stirrup. Okay, the maximum, the yield stress. Okay, and then there's this AV over S ratio that's running around. For incline stirrups, it's the same equation, except now you have sine alpha and cosine alpha, where alpha is some angle greater than 45 degrees. Okay, in this one, we're not allowed to take the tensile strength of the stirrups, anything greater than 60,000. Okay, and then we're going to pick our area, our AV, whether it's a number 3 or a number 4 or a number 5, and generally assume a U stirrup, and then we're going to find the corresponding spacing for what's happening on this. Now, I know it's a lot of steps that I just kind of showed you in this procedure, but we're not done yet. Okay, it's really not that bad. It's basically a rehash of everything that we talked about in the last video. Okay, but again, kind of putting it in a concise setup here. Okay, so item 5, we're going to design for the minimum web reinforcement first. Okay, and this is at every point on that graph where our applied shear is greater than VC over 2 times phi. Okay, except for slabs, footings, joists, and small beams shallower than 10 inches, 2.5 times the flange thickness, or BW2. That's that exception table that I showed you in the last video, where we're controlled by an AV minimum. We have to obey AV minimum of 50 BWS over FY, greater than or equal to 0.75 square root F prime C BWS over FY. Okay, so this is that check that we were talking about in the last video. If you don't remember this, go back and take a look at the video. Okay, we spent a fair amount of detail and a amount of time on kind of explaining some of those concepts. Okay, now we want to check our spacing, S max, for vertical stirrups. So if VS is less than, so this is our lightly shear load, less than 4 root F prime C BWD. These are our requirements, D over 2, 24 inches, or AVFY over 50 BW. Okay, and we're going to choose the smaller of that limit. And then if we're larger than that, if our VS is heavily loaded in shear, then basically our S max is halved. It's now D over 4, and our S max is 12 inches instead of 24, and then this check is still the same. Okay, now, and from a design standpoint, kind of as a rule of thumb, a 3-inch or a 4-inch is a practical minimum for placement. Okay, you start getting anything closer than that, 1 inches or 2 inches, and the bars are practically on top of each other. It's hard to tie them. You start getting into trouble with, clear spacings for aggregates, to fall through. If you go back and look at some of the detailing that we talked about in our flexure discussion, there were criteria based on aggregate size for how close bars could be together. You start getting into problems. 3 inches or 4 inches is about as small as I like to go. Because if I end up needing, my calculations show that I need 2 inches spacing because I chose a number 3 bar, it's probably in my best interest to go use a number 4 instead and move that spacing up to some other limit that's a little bit more practical. It's an indicator that your bar size is probably too small for what you're wanting it for the shear load that you're wanting it to hold. And so I'm going to be kind of mindful of that. All right. So here's where it all kind of comes together, okay? If we look at, okay, we're going to plot the curve for spacing, okay, and decide the actual spacings for web reinforcement. So what I've done is I've taken kind of this this is that diagram that we had, that we drew before. Okay, this for simply supported, half span, if you will. The shaded region is my VS. Okay, and the way that I start figuring out my calculations, again, remember, we've got 3 regions that we're looking at. This region, stirrups are not required, all right, because we're less than phi VC over 2. Okay, and again, and then from this region, we're running at S max, which is this guy. The maximum spacing is going to control, and then from here to here, my spacing is going to change. So what happens is, as you get to higher shear loads, which is what we had over here, okay, my spacing has to get smaller and smaller. Okay, and then as I move away and the shear decreases, I can start to change my spacing and make it a little bit wider. Okay, and so what happens is I can kind of start to plot this curve, if you will. Okay, and this is kind of the design standpoint. Okay, now what I normally do is I will set my diagram up, it'll look something kind of like this, in which I draw this to scale, and I go in and I run my calculations that for a 4-inch spacing of a number 3, I would get a specific value for the VS. Now in this particular example, we're just saying that, a 6-inch spacing gets me that point, okay, gets me the VS that I need, and then it shifts up to a 7, and then up to an 8, and a 9, and a 10, and all the way on up. And I can kind of start building these points. Okay, so if this is 6, I think this was 7, this was 8, this was 9, this was 10, and so forth and so on, depending on what S max is. Maybe this goes up to 12 or 16 or something, but I can start to kind of pick these things off. And what you want to do when you start to choose these is choose them in such a way that, that it's not like, one bar at 6 inches and the next bar at 7. You want to have, like, maybe you put 2 at 6s, and try to kind of make it uniform so that the guy that's building this doesn't have, 17 different spacing requirements on every stirrup, and it makes the quality check a whole lot easier. Break this down into some convenient pattern of, 2 or 3 different spacings along the length of the beam if you can. You can also kind of pick your values in such a way that, and I didn't do that in this particular example, but a 7-inch spacing is kind of an ugly number, right? What we like to do is, if I can get something so that it's a multiple into, 24 inches, so a 3-inch spacing is good because 8 of those gets me 24 inches. A 4 is good because it gets me 6. A 6 is good, an 8 is good, and then we can get into a 12. Those are pretty convenient spacings for laying this thing out, because what happens after 2 feet, the pattern can repeat itself. If I start trying to use a 5-inch spacing or a 9-inch spacing, as I move down the beam, it gets kind of hard to detail and figure out where these need to be as you start to kind of look at. But that's kind of what we're doing, is we're starting to kind of lay these in such a way. Now, this curve, I could do a 6-inch spacing all the way over to here if I wanted to, but I would be using a whole lot more stirrups, right? Because what you're trying to do is that spacing curve, when you calculate the VS or the S from the shear that you require, okay, you're generating this curve, okay, and you're trying to basically approximate that curve as best you can with these even increment lines, if you will. And so there's kind of an art to the way that you start to kind of lay this stuff out. And like I say, when you get to the example, and at the end of the packet, you'll start to see this. I actually give you the points of the curve, and you can start to kind of play with this a little bit. But that's the general curve that we're wanting. So once I get to this line, okay, now S max is controlling, and then from here, nothing is required. But again, I like to just run this line continuous anyway, out past, and just carry this S max on over, and we can start to kind of see what's happening there. All right. So now at this point, in my class, we would start looking at kind of a design example, and I'll kind of show you, kind of walk you through the thoughts that are happening in this. All right. So for our design example, again, we're doing a simply supported beam, 30-foot WU. So you don't need to see that anymore. But the general approach is our goal is to come up with the spacing associated with these locations, okay? That for our section, our beam is 12 inches, the height is 36, and the length of 30 feet, or 360 inches, okay, with the spacing requirements from that. So again, what we've done is we've calculated the curve that at a space, at the center line, the minimum spacing is 2 inches, which that's kind of an indicator my stirrup size isn't right, but we're going to go with it just because this is kind of an exercise in how to lay this thing out and start choosing spacings. At 48 inches from the left, your V would be corresponding to, a 6.5-inch spacing required. 96 inches from the left, 15 inches is my spacing, 144 is 27, and 192 is 54. Now, obviously, at these points, this is that curve that's coming up on the diagonal. It's this curve, right? And so what we've done is we plotted the points on up the page, okay? But notice that you're going to be bound by this S max limit, so we're going to have to figure out what S max is and draw that line in. But that table gets you this curved line here as you start to lay this thing out. Okay. So again, we're going to just for the sake of this exercise, we're just going to assume that S max is calculated as 16 inches. And again, if you know B and D, you can calculate what these dimensions are from, is it heavily loaded in shear or lightly loaded in shear? You can pull this off of the ACI requirements pretty easy. Okay. Again, the hardest part of this is figuring out, well, what spacings do I need? Okay, so what we want to do is we want to determine the required stirrup spacing for a half span based on this data. Okay, so the depth D we're given. Now we're gonna have to, we gave you B and H, so you'll have to make some assumption about the depth, and we can use that cover limit H minus 2.5 inches or H minus 3.5 for 2 layers of steel, whatever, that will get us that value. Okay, and then we're going to plot the spacing curve, which is the data that comes out of this, and then we're going to determine the even increments of spacing versus position for 1 inch spacing. Okay, and then we're going to start to kind of consolidate these things. So what I do is I start out with kind of a graph that looks like this, and in the packets that the students are working, you guys will have this page, but if not, you can just kind of make something fairly simple like this. And so I'll kind of walk you through kind of how I start to do this. Okay, so the first thing that I do is I notice that, I've plotted from 0 to 18, it's even increments on this. And I know that at 16 inches, there's kind of this line that comes across here. Again, this is very sloppy, very ugly, but I'm just kind of doing kind of a crude. That's going to be your S max, right? That we said he was listed as 16 inches, whatever you found ACI to be. So you'll lay him. And then the next points that we have are coming in and figuring out, okay, for my minimum spacing tables, we had a point, if I put this over here where you can see it. And this data, again, you can generate the data from the equations yourself, that at 0 inches, which is here, okay, we had a spacing of 2, so I'll put a dot there. Okay, at 48 inches, which is this point, we had 6.5. So now we're looking at being somewhere like right there. Okay, and then at, what do we have? We have 96, I'll do one more to get this on here. 96, it jumps up to 15. Okay, so we're almost to our maximum limit, but not quite. Okay, and then our last one, if you look, is 144 at 27. So at 27, here's my 144 line. We're now way the heck up there somewhere. Right, so you can see that if I kind of connect the dots here, I get a curve that looks something kind of like this. Okay, and then I get a curve that looks something kind of like this, and then this guy kind of takes off and looks something like that. That's your S curve. Your S is a function of X, is that curve. Okay, and so again, all we're trying to do is come up with the lines that make, decent arrangements of stirrups on this. Okay, so at this point, if you draw this to scale, you can read off that, okay, well, starting at, at 96 inches, I was at 15, and then at 108, clearly we're at 16, where the maximum is controlled. Somewhere in between 96 and 108, this thing can start to proceed off of the S max. So this is kind of that third point. So a lot of times what I'll do is I'll just come over and I'll say, okay, starting at 108, we'll make everything 16, and then we'll just build our lines. But the question becomes, well, how do you decide what to do on this? And so what I start to do is I start to kind of look at drawing horizontal lines at all these different increments. And we can kind of start to look. So if I took a 2-inch spacing, I could go all the way over to there, right? And then at that point, I'm adequate for 4-inch spacing. I can come all the way over to there. And then if I took a 6-inch spacing, depending on where you wanted to go, if I went to, here, I'd only be at 7 inches. If I go up to here, it's 8 inches. If I go all the way up to here, it's 10 inches. All the way up to here, it's 12. So maybe I decide I want to do this guy as, we could go, let's just go to 8. We'll put him there. So there's my 8. Okay, and then from here, I'm now at 8. I can go all the way over. It seems like 12 is kind of a pretty reasonable limit. Something that kind of looks something like that, right? And then so forth and so on. And then at this point, I go 12, and I go all the way over to 16 at this point. And so that would be your spacing curve. So there's a 2-inch curve, and this says I go to about, 18 inches. And then this is my 4-inch spacing, and I go from the end of that one to, 30 or whatever it scales out to be. And this is how you kind of build these curves. Okay, now again, what you don't want to do, on this, because recognize that every one of these stirrups are very tightly spaced here. I don't want to, I could take a 2-inch spacing and go all the way over here to S max and come up and do that, and that would be completely valid. But look how much you've overestimated that curve by doing that. You would be doing a whole lot more extra steel install. There'd be a lot more stirrups required, and it becomes a whole lot harder to be able to kind of work on it. But that's the basis of the approach that we're going to use for establishing these spacing curves. And that's what I want you guys kind of getting some practice doing. Now, there are an infinite number of possible answers that satisfy this. Again, try to think of yourself as that 24-inch rule, that you want these to be some factor of 24 inches, so that every time I end, I do things for 24 inches at a time. So 3 number 8s is 24 inches. I put 3 stirrups in, I'm 2 foot away, and then I can continue on. Okay, whereas with 2 inches, I would need 12 of them, and 4 inches, I would need 6 of them. So those rules that I showed you, kind of rules of thumb, and we're going to kind of work on, keep that 24-inch special number as kind of a rule of thumb in the back of your mind as you're looking to lay this thing out. Okay, once you have that, then you can come in and you can say, all right, from I can draw the bottom of this, and I can just basically, I can extend these lines down. And so I know that in this region, I would need, if this was 18 inches, I would need, this is a 2-inch spacing, you would need 9 of them there. So you can start getting kind of a quantity check. And then from, 18 to 40, at 4 inches, that's, I probably need 6 more at 4-inch spacing to get me out to here. And that's the way that you start to lay this thing out. And then, when you do your detail drawing, you can actually draw these in at true scale or whatever. But that's the way that you can lay this thing out. And eventually, that as a running dimension, at position of 9, at a position of, 9, I said 9 stirrups, at a position that I do 9 at 2 inches, and then I do 6 at 4, and I can build this diagram all the way out. And then eventually I get out here in the middle somewhere. Okay, and now I'm at, at my S max is starting control. That's my 16 inches max, and then you can quantify this. And so this is something that some of the steel detailers will start to do when they're reinforcing, because in design, every one of these stirrups is designed the same way. Generally, you don't mix and match. I don't have number 4s here and then number 3s. We don't like to do that very often. Maybe kind of a strange circumstance where we do that, but we make them all the same. We just vary the spacing so I can use the same bar. And now the people in the shop can mass produce these stirrups to be able to meet your needs, and then you as the engineer control that stirrup by adjusting the spacings accordingly. But that's the approach to dealing these stirrup spacing curves on those. All right, so with that, I think we'll end the video there. I hope it hasn't been too confusing for you. I hope that makes sense. As always, please toss us a like on the video if you found it helpful. If not, leave us a comment. Let us know what we can do better or differently, and we'll keep putting these things out. Remember to subscribe to the channel. Otherwise, have a great afternoon, and we will talk to you all later. Happy engineering.